Just imagine for a second. A massive firestorm sweeping away everything in its path. A shockwave capable of turning concrete buildings to dust from miles away. Temperatures hotter than the core of our sun. And now, wrap your head around an amazing fact. This unimaginable fury of nature is born from an object so small we can't even see it with the most powerful optical microscope. From an atom. Why does a tiny, invisible particle hold the rage to destroy entire cities? Where does this energy even come from? For the longest time, we thought of matter as something completely dense, motionless, and dead. A solid foundation of reality. But today, we're going to look past that illusion. We'll figure out what invisible springs are hidden inside the smallest building blocks of the universe, and why breaking them releases the primordial fire of the cosmos. Walk up to the nearest wall, or just put your hand on the desk you're sitting at right now. Knock on it. Feel the resistance. Wood, metal, plastic, or concrete. All of it feels incredibly solid to us. Monolithic. Our brains, shaped by hundreds of thousands of years of evolution, have taught us to completely trust our sense of touch. If an object doesn't let your hand pass through it, it means the space inside that object is filled with matter. Packed tight, without any gaps or empty spaces. This idea seems so logical to people that even the ancient Greek thinker Democritus, who lived 400 years BC, came up with the concept of a fundamental building block of the universe. One day, while lost in thought on the seashore, he noticed the sand. From a distance, a sandy beach looks like a solid, continuous line. But if you walk right up and grab a handful of sand, it becomes clear that it's made of millions of individual grains. Democritus applied this logic to the entire universe. He guessed that if we started splitting a piece of rock in half, then in half again, and did this millions of times, eventually we'd hit a tiny, absolutely solid particle that couldn't be divided anymore. For him, and for dozens of generations of scientists after him, the atom was the ultimate standard of impenetrable density, the most solid object imaginable. And this comforting illusion lived on happily right up until the end of the 19th century. By then, science had made huge strides, but physicists still pictured the atom as a sort of evenly charged, solid sphere. British researcher J.J. Thomson, who discovered the negatively charged electron in 1897, proposed his own model of how matter is built. His colleagues jokingly called it the plum pudding model. According to Thomson's idea, an atom was a cloud of positive charge with negative electrons evenly scattered inside it, like sweet raisins in a dense sponge cake. Everything made sense. Everything was filled up, and every particle was right where it belonged, keeping the universe balanced. But the problem is that fundamental science has no patience for guesses you can't test in practice. In 1911, Ernest Rutherford, a brilliant New Zealand physicist, decided to run an experiment that forever changed our understanding of what we're made of. Rutherford and his talented assistants Hans Geiger and Ernest Marsden came up with an incredibly elegant setup. They took an insanely thin sheet of gold foil. It was only about 400 atoms thick. If you want to probe the structure of matter, you need the thinnest barrier you can possibly make. And gold has a unique property. It can be rolled into sheets so thin they're almost see-through. Next, the scientists started shooting alpha particles at this gold foil. An alpha particle is basically a heavy, positively charged microscopic bullet fired off by a radioactive element. Around the gold foil, the researchers set up a circular screen coated with a special chemical, zinc sulfide. Whenever an invisible alpha particle hit this screen, it produced a tiny flash of light. The logic behind Rutherford's experiment was totally flawless. If the atom is a dense pudding, as Thomson claimed, then heavy alpha particles flying at massive speeds should punch right through the gold foil. Think of it like a cannonball blasting through a sheet of soft cardboard. The cannonball might veer slightly off its straight path because of the material's resistance, but it absolutely has to go through. A long, exhausting experiment began. The researchers sat for hours in a pitch-black lab. They had to wait at least half an hour just for their eyes to adjust to the dark enough to spot the faint flashes on the screen. And at first, everything went exactly as classical physics predicted. The vast majority of the particles really did fly through the gold barrier in a straight line, as if it wasn't even there. But at some point, something unimaginable happened. About 1 out of every 8,000 alpha particles behaved completely bizarrely. It didn't punch through the foil. It bounced off at a sharp angle and sometimes even flew straight back, right toward where it was fired from. Ernest Rutherford himself later described his scientific shock with one very vivid phrase. He said it was just as incredible as if you fired a massive artillery shell at a piece of thin tissue paper, and the shell suddenly bounced off it and hit you right in the forehead. It completely defied all common sense. If the atom is a soft, evenly spread out cloud, then what exactly were these heavy, insanely fast alpha particles bouncing off of? The answer Rutherford arrived at after a lot of thought turned physics upside down. He realized that the atom is almost entirely made up of empty space. An absolute, completely empty void. The entire mass of the atom, its entire positive charge, wasn't smeared out across its volume like people used to think. Instead, it was concentrated in one unfathomably tiny point right in the center. Rutherford called this central point the atomic nucleus. And the electrons, he guessed, orbit this nucleus from very far away, just like planets orbiting the sun. A little later, the Danish physicist Niels Bohr refined this model and backed it up with math. It's this exact, elegant system of orbits that we see today on the covers of middle school chemistry and physics textbooks. But let's pause here and break this down a bit more, because the human brain absolutely refuses to process dry academic numbers. We need vivid comparisons to grasp the true depth of this emptiness. Just picture a normal hydrogen atom. It's the simplest chemical element in the universe. One nucleus in the center, and one electron in orbit. Let's mentally scale up the nucleus of this atom to the size of a regular apple and put it, say, right on the center mark of a massive football stadium. So, if the nucleus is an apple sitting on the green grass, right in the middle of the field, where would the electron be? In the stands? In the upper decks? Go way bigger. The electron, which in this scaled-up model would be the size of a microscopic speck of dust, would be zipping around its orbit miles away from our apple, maybe somewhere on the very outskirts of the city. And what's between this speeding speck of dust and the apple in the stadium? Absolutely nothing. No air, no invisible ether, no hidden matter, just a vacuum. Based on this scale, scientists calculated that any atom is 99.999% made up of absolute, completely empty space. Think about that for a second. You, me, the desk in front of you, the walls of your room, planet Earth, and distant galaxies. All of it is almost 100% a gaping nothingness. If, by some sci-fi magic, we could suck all this empty space out of the bodies of every person alive on the planet today, all of humanity, all 8 billion people, could be squeezed down to the size of a single sugar cube. And that one sugar cube would weigh hundreds of millions of tons, because all the mass would still be there. Only the distance between the particles would disappear. But here, a thoughtful listener might ask a totally logical and natural question. If matter is just pure emptiness, why aren't we falling through the floor right now? Why, when we clap our hands hard, do they bounce off each other with a loud smack instead of passing right through like 2 clouds of smoke? After all, empty space should easily pass through empty space. This is where the story takes a fascinating turn. It turns out that what we experience as solidness or physical touch is also a massive illusion, masterfully crafted by our nervous system. In reality, we never actually touch anything in the literal sense of the word. The secret lies in the electrons zipping around on those insanely distant orbits around the nucleus. They carry a negative electrical charge, and when you bring your hand close to the surface of a disk, the electrons on the outer shell of your skin's atoms inevitably get closer to the electrons on the outer shell of the wood or plastic atoms. According to the fundamental laws of electromagnetism, like charges repel each other. But that's only half the truth. In quantum mechanics, there's an ironclad rule discovered by the Austrian physicist Wolfgang Pauli. It's known to science as the Pauli exclusion principle. To explain this incredibly complex concept in simple terms, this principle states that 2 fermions, and electrons belong to this class of particles, absolutely cannot occupy the same quantum state in the same space at the same time. They physically can't stand being crowded. When the atoms of your hand get right up close to the atoms of the desk, their invisible electron clouds start to overlap, and in that moment, a fierce quantum resistance kicks in. The electrons violently push each other away, demanding to keep their personal space untouched. It's this insurmountable force of electromagnetic repulsion and quantum exclusion that your brain interprets as the feeling of a solid, impenetrable object. When you sit on a chair, you aren't actually touching its surface. You are literally levitating a tiny fraction of a millimeter above it, safely supported by an invisible cushion of magnetic fields and strict quantum laws. But why are we spending so much time going step by step over electrons and the illusion of empty space if our main goal is to understand the terrifying nature of a nuclear explosion? The answer is simple. We need to clearly separate the outer shell of reality from the true source of primordial power. Electrons, chemical bonds, complex molecular structures, all of this is solely responsible for the calm, macroscopic world we're used to. When a campfire burns in the woods, when gunpowder explodes, or when dynamite detonates, that's just electrons rearranging themselves on their orbits. They break old bonds and create new ones. Energy really does get released in these normal chemical reactions, but the amount is laughably small by the standards of how the universe is built. The real monster, the one capable of turning cities to dust, is hiding right in the center, inside that tiny apple sitting all alone in the middle of a massive, miles-wide empty stadium in the atomic nucleus. That is where, in this microscopic speck, almost the entire mass of the atom is concentrated. The density of this mysterious structure is far beyond human imagination. If you could scoop up a regular teaspoon of the stuff that makes up an atomic nucleus, that spoon would weigh about 1 billion tons here on Earth. That's the weight of a giant mountain range compressed into a volume that easily fits in the palm of your hand. All the mass, all the fundamental heaviness of the universe is packed into these tiny islands, separated by endless oceans of absolute void. And to understand how to extract energy from this invisible speck of dust, energy capable of melting concrete and turning metal into gas, we have to look inside the nucleus itself. But when physicists peeked inside in the early 20th century, they found a paradox that almost drove them crazy. They saw a structure inside the nucleus that, according to every law of nature known at the time, had absolutely no right to exist. The nucleus should have blown itself to pieces the very fraction of a second it formed. Yet, it continued to exist. And it was exactly in this impossible internal tension, in this illogical force locked inside matter, that the secret to the most terrifying mechanism in the history of the universe was hiding. So what is this paradox? And how does it work? We'll talk about that in our next chapter. By the early 1930s, the picture of the invisible quantum world slowly started to clear up. Scientists finally realized that the atomic nucleus, that tiny, super-dense speck of dust in the center of the atom's giant void, wasn't some monolithic, indivisible object at all. It was actually an incredibly complex structure made up of even smaller parts. Today, we call these basic parts by the umbrella term nucleons, which comes from the Latin word nucleus, meaning core. Physicists managed to figure out that there are two main types of nucleons, protons and neutrons. The proton was discovered by the same tireless Ernest Rutherford back in 1919. But the neutron hid from researchers a lot longer. It was finally spotted by the British physicist James Chadwick in 1932. This discovery became a massive milestone in science. The main difference between these two particles, and the most critical one for our investigation, is their electrical charge. A neutron, as its name very logically suggests, is electrically neutral. It doesn't carry a positive or a negative charge. It just has a certain mass and peacefully coexists with other particles. But the proton is a completely different story. Every single proton has a clearly defined positive electrical charge. And right here, in this seemingly dry academic detail, the greatest physical paradox of the universe is born. A paradox that you absolutely have to understand if you want to grasp the nature of a colossal nuclear explosion. Let's take a mental trip back to the late 18th century. In 1785, the brilliant French physicist Charles-Augustin de Coulomb ran a series of genius experiments and laid out a fundamental law of electrostatics, which every middle schooler today knows as Coulomb's law. The core idea of this law is extremely simple to grasp, but its consequences are truly epic. Coulomb's law states that opposite electrical charges, meaning a plus and a minus, try to pull toward each other. But like charges, like two pluses, always violently push each other away. And the strength of this interaction is described by a very strict mathematical formula. In plain English, the force of electrostatic repulsion between two positively charged particles is inversely proportional to the square of the distance between them. What does that sentence mean in real life? It describes an exponential explosion of power. If you take two positive charges and bring them closer together, cutting the distance between them in half, the force pushing them apart doesn't just double, it quadruples. If you cut the distance by a factor of 10, the particles will push away from each other 100 times harder. The closer they get, the more insurmountable the invisible wall pushing them apart becomes. Now let's go back to our atomic nucleus and look at it through the lens of Coulomb's law. Inside the nucleus, packed into an unimaginably tiny space, are protons. In the nucleus of the oxygen we breathe, there are 8. In an iron nucleus, there are 26. And in the nucleus of a heavy element like uranium, there are a whopping 92 positively charged protons all at once. And they are all squeezed into a volume whose diameter is measured in femtometers. Just so you can picture this scale, 1 femtometer is 1 quadrillionth of a standard meter. That's a 0, a decimal point, 14 more zeros, and a 1. The distances between the protons inside the nucleus are so laughably tiny that the denominator in Charles-Augustin de Coulomb's formula is basically approaching 0. As a result, the force of their mutual electrostatic repulsion skyrockets to absolutely astronomical, terrifying numbers. To really feel this force on a physical level, let's do a thought experiment. I'm sure many of you have held powerful neodymium magnets in your hands at some point. Imagine taking 2 of these shiny metal cylinders and trying to push their identical poles together. You start bringing your hands closer. At first, the resistance feels light, but as the magnets get closer, it builds up. When there's just a couple of millimeters left between them, you feel like a dense, bouncy ball has formed between the metal. The magnets shake in your fingers, trying to slip, twist, and rip themselves away. Your muscles tense up. You're spending real physical energy just to hold them next to each other. Now imagine that instead of 2 magnets, you are holding 92 unbelievably powerful sources of repulsion. And you're trying not just to hold them next to each other, but to crush them together into a space billions of times smaller than a single grain of sand. Physicists calculated that the force of Coulomb repulsion between 2 neighboring protons inside an atomic nucleus is equivalent to a weight of about 10 kilograms. 10 kilograms of pressure applied to an object that is a subatomic particle. On the scale of the quantum world, that's not just a massive force, it's apocalyptic pressure. It's a tension that surpasses anything we could ever encounter in our everyday macroscopic reality. All of this leads to one mind-numbing conclusion. According to all the laws of classical physics, the atomic nucleus has no right to exist. It should instantly explode. The 92 protons in a uranium nucleus, experiencing a fierce mutual hatred caused by their identical charges, should blast apart in all directions at speeds reaching a significant fraction of the speed of light. The nucleus should rip itself to shreds the very fraction of a microsecond it tries to form. If the world were governed solely by the forces known to science at the start of the 20th century, our universe would look completely different. It wouldn't have any complex chemical elements. There would be no carbon, no oxygen, no silicon, no gold. The entire endless cosmos would just be filled with a thin fog of lonely hydrogen protons drifting infinitely far apart. After all, a hydrogen nucleus consists of just one single proton with nothing to repel. No stars, no solid planets, no biological cells, and obviously, no humanity could have ever come to be. But you are listening to this story. I am telling it to you. Our planet is flying through outer space, and blood is pumping through our veins, containing iron with its 26 tightly packed protons in every atom. Matter exists. It's stable. The desk in front of you isn't exploding in a blinding flash this very second. It was exactly this fact that drove researchers crazy. How is this possible? What is holding back this primordial chaos? The first logical thought was to look to gravity. After all, gravity is a universal force of attraction, famously described by the genius Isaac Newton. All objects with mass attract each other. Maybe the mass of the protons makes them attract each other, canceling out their electrical repulsion. But basic math shattered that hope into a million pieces. The mass of a single proton is so incredibly tiny that the force of gravitational pull between two neighboring nucleons turns out to be laughably weak. Just so you understand the gap in scale, the force of electromagnetic repulsion is stronger than the force of gravitational attraction between two protons by a factor of 1 followed by 36 zeros. Gravity is totally powerless on a quantum level. It's like a faint whisper trying to drown out the deafening roar of a jet engine. It has absolutely no way to keep the nucleus from falling apart. By the mid-1930s, it became crystal clear. Right in the heart of matter, a completely different force is at play. A mechanism that humanity hadn't even suspected existed throughout its entire history. Nature had hidden invisible steel cables inside the atom that ruthlessly bind the particles together, refusing to let them fly apart under the power of Coulomb's law. Realizing this fact is the absolute key to understanding the nature of a nuclear explosion. We're used to thinking that a nuclear bomb creates energy out of nowhere. But the truth is, a giant explosion is just the release of that exact electrostatic repulsion that was artificially locked up inside the nucleus billions of years ago. All that rage, all that unbearable heat and blinding light that we see in nuclear test footage, that is the pure, primordial hatred the protons have for each other. It's their ancient, unquenchable desire to fly apart, breaking out of their cramped quantum prison. When detonation happens, you aren't seeing a new force being born. You're seeing the sudden triumph of Charles-Augustin de Coulomb's law. You're watching the protons finally get their long-awaited freedom and dart away, sweeping away everything in their path. But for this spring to uncoil, it first had to be compressed somehow. And that unknown mechanism, those invisible chains that keep these charged particles together against all logic, must possess truly monstrous strength. They have to be stronger than the most extreme repulsion in the universe. Physicists found themselves facing the ultimate riddle. They had to find, describe, and understand a new fundamental force of nature, one that only works at distances of billionths of a millimeter, but still manages to dictate the architecture of the entire universe. A force that allows solid matter to exist. This mystery had to be solved to take the next step in understanding reality. And so, science came right to the edge of discovering a phenomenon we now call the strong nuclear force. In the next chapter, we're going to travel to the very bottom of the quantum well to meet the true titans of the micro-world. We'll find out exactly how these invisible guards lock the protons down, and the incredible price matter pays for this fragile illusion of stability. In the early 1930s, the global scientific community found itself at a massive intellectual dead end. Physicists stared at the mathematical equations describing the atomic nucleus and realized they had hit an unbreakable wall. As we figured out earlier, positively charged protons inside the nucleus feel a colossal electromagnetic hatred for each other. They should be flying apart at near light speed. But they aren't. The matter around us remains stable. The brilliant German physicist Werner Heisenberg, one of the founders of quantum mechanics, spent sleepless nights trying to find a way out of this paradox. It was totally obvious that neither gravity nor electromagnetism could explain how the micro-world was built. Scientists had to accept a deeply terrifying but unavoidable fact. Down there, in the unthinkable depths of the atomic nucleus, a completely different fundamental force of nature, one totally unknown to humanity, was at work. And this force had to be truly titanic to hold together something that so desperately wanted to tear itself apart. The Japanese theoretical physicist Hideki Yukawa shed light on this dark mystery in 1935. He proposed a concept that forever changed our understanding of the universe's architecture. Yukawa stated that a special, hidden mechanism was responsible for the stability of matter, which he called the strong nuclear force. The word strong here isn't just used for dramatic effect. It's a harsh physics term. The strong force is the most powerful fundamental force that exists in our universe. It is roughly 100 times stronger than the electromagnetic repulsion we talked about earlier. But how exactly does this incredible force work? To understand that, we'll have to dive a bit into the weird and counterintuitive world of quantum physics. In our daily lives, we're used to thinking of a force as some kind of invisible field that just pulls objects together or pushes them apart. We picture gravity or magnetism as invisible strings. However, on a quantum level, nature operates totally differently. Any interaction between particles happens by exchanging other, even smaller particles, the quanta of that interaction. Let's use a thought experiment to visualize this process. Imagine two ice skaters standing on perfectly smooth ice, facing each other. One of them is holding a heavy medicine ball. The first skater throws this ball hard to the second one. Thanks to the law of conservation of momentum, the moment the first skater throws the ball, they'll roll backward. And when the second skater catches this heavy projectile, the momentum will knock them backward too. So, just by tossing a ball back and forth, they will slide away from each other in opposite directions. This is exactly how the force of repulsion works in the quantum world. Particles exchange photons and push away from each other. But how can exchanging something make objects attract? Yukawa guessed that the nucleons in the nucleus continuously exchange special particles which he called mesons. To visualize attraction through exchange, imagine those same two people. But now they are fighting over a heavy kettlebell that is tied to both of them with a strong rope. They are snatching it back and forth with such insane speed, millions of times in a fraction of a second, that this continuous exchange permanently binds them together. They simply can't walk away from each other because the process of passing this binding particle requires them to stay constantly and very closely nearby. Hideki Yukawa calculated the mass of this hypothetical carrier particle, and a few years later, scientists actually found it in cosmic rays. It was named the Pi meson. It was an absolute triumph of theoretical thought. It turned out that protons and neutrons inside the atomic nucleus aren't just sitting next to each other like potatoes in a sack. They are continuously, at an unimaginable speed, tossing these pi mesons back and forth. It's this frantic, non-stop quantum dance that creates the iron grip that stops the nucleus from blowing itself to pieces. However, the strong nuclear force has one incredibly specific and absolutely crucial quirk. This quirk is the key to understanding why atomic nuclei can't be the size of a baseball or a planet. The thing is, the electromagnetic field that forces protons to repel each other works over massive distances. Its strength fades gradually, melting away into space. But the strong nuclear force has an incredibly strict range limit. It acts like an invisible, unbelievably tight rubber band. If two protons are more than 2 or 3 femtometers apart, the strong force literally doesn't work at all. It drops to absolute zero. The particles just don't feel each other across the quantum void. But the moment they get within about 1 femtometer of each other, which, as a reminder, is 1/4,000,000th of a meter, that rubber band instantly snaps into place. The strong attraction sharply spikes and deadlocks the particles together, completely overpowering their mutual electrical hatred. But that's not all. If you try to squeeze these protons even harder, pressing them flush against each other, the strong force suddenly changes its personality and turns into an impenetrable wall of repulsion. It doesn't let the nucleons melt into a single shapeless mush. It strictly keeps them at a very specific distance, preserving the structure of the nucleus. Let's put these facts together into one clear picture using a vivid analogy. Imagine a group of several dozen people who absolutely despise each other. They carry the same electrical charge and have a burning desire to run as far away from each other as possible. But someone comes along and tightly binds them together with dozens of layers of the strongest rubber bands. These bands are the strong nuclear force. The people inside this bundle are squirming, shoving, trying to break free. The tension inside this group is off the charts. The bands are stretched to their absolute limit, vibrating from the colossal internal pressure, but they still hold up against the strain and keep the group from falling apart. That is exactly what an atomic nucleus looks like from the inside. It's not a calm, solid little ball of matter. It's a tiny, unbelievably dense knot of pure rage and colossal physical tension. It is a battlefield of an endless war between the two most powerful forces in the universe: electromagnetic repulsion trying to tear the nucleus apart, and the strong nuclear force ruthlessly binding its pieces into a single whole. In this complex architecture, we can't ignore another crucial player. James Chadwick, as I mentioned earlier, discovered the neutron. But why did nature even need this particle, devoid of any electrical charge? For years, its role wasn't entirely clear. But in light of the discovery of the strong force, everything fell into place. The neutron is the ultimate, flawless quantum glue. Think about it. When you add a new proton to the nucleus, you inevitably increase the total force of Coulomb repulsion because protons repel each other. But if you add a neutron, there's no extra electromagnetic repulsion because the neutron has zero charge. Yet the neutron, being a full-fledged nucleon, is perfectly capable of emitting and absorbing those p mesons. It actively participates in the strong nuclear force. The neutron is pulled toward protons and other neutrons by its rubber bands, pulling the nucleus tighter, but without pushing anyone away. It acts as a buffer, a spacer that dilutes the concentration of positive charges and adds stability to the nucleus. That's exactly why light elements like helium or carbon usually have an equal number of protons and neutrons. But as we move down the periodic table to heavier elements, there are so many protons that their repulsion threatens to destroy the entire system. And to keep this monster under control, nature has to pump more and more neutrons into the nucleus. A gold nucleus, for instance, has 79 protons and a massive 118 neutrons. This extra quantum glue is completely necessary to cancel out the growing hatred of the charged particles. And here we arrive at the most intriguing philosophical takeaway of our current discussion. What we perceive in our daily lives as calm, unshakable, motionless matter, a rock, a piece of metal, a glass of water, is, on a fundamental level, the arena for the most violent and intense conflicts in the universe. Every single atom in your body exists solely because of a razor-thin, incredibly fragile balance between all-consuming attraction and crushing repulsion. An atom's nucleus can be compared to a set trap or a spring that was compressed to its absolute limit billions of years ago in the furnaces of ancient stars, carefully locked in place by the invisible latch of the strong force. The energy hasn't gone anywhere. It didn't dissolve into time. It's still right there, inside that coiled spring, waiting for its moment. But where exactly does this energy come from? How does the tension of invisible fields convert into that monstrous destructive power we've been talking about from the start? To answer this question, we have to face yet another paradox of the quantum world. A paradox that breaks the very foundations of classical math. We're used to believing that the whole is always equal to the sum of its parts. But the quantum world plays by different rules. Down there, 2 plus 2 can actually be less than 4. Where does matter disappear to when a nucleus is assembled? And why is this missing mass the key to understanding a nuclear explosion? Let's turn the page and figure this out in our next chapter. Let's forget about complicated quantum paradoxes for a few minutes and return to our familiar, understandable, and predictable macroscopic world. To a world governed by the unbreakable rules of basic arithmetic. The foundation of our everyday thinking is a simple statement. The whole is always exactly equal to the sum of its parts. If you take a normal basket and put 4 apples in it, each weighing exactly 100 grams, the total weight of those apples will be exactly 400 grams. Not a gram less, not a gram more. It seems so obvious that we don't even think about it in our daily hustle. This intuitive principle was elevated to the status of a strict scientific law way back at the end of the 18th century. The brilliant French chemist Antoine Laurent de Lavoisier ran a series of meticulous experiments weighing substances before and after chemical reactions. He formulated the law of conservation of mass, which states that the mass of the substances entering a reaction is exactly equal to the mass of the substances resulting from that reaction. Matter cannot appear out of nowhere, and it absolutely cannot vanish into nothingness without a trace. If you burn a log inside a sealed, airtight container, the ash, smoke, and gases left inside will weigh exactly the same as the original log and oxygen did before the fire started. This was the absolute rock-solid foundation of classical science. But does this law apply to those invisible depths of matter hidden in absolute emptiness that we talked about in the previous chapters? In the early 20th century, physicists genuinely believed it did. They assumed that no matter how tiny protons and neutrons were, they were still material objects, which meant they had to obey the laws of Lavoisier and Newton. To test this assumption, researchers needed to figure out how to weigh individual atoms and their components. And this is where the British physicist Francis William Aston steps onto the historical stage. In 1919, working at the famous Cavendish Laboratory in Cambridge, he built a device that sparked a genuine revolution in measuring the micro-world. This device was called a mass spectrometer. How it works is quite elegant and deserves a closer look. How do you weigh something you can't see? Aston came up with this method. First, the atoms of the substance being studied are stripped of some of their electrons, turning them into positively charged ions. Then, these ions are accelerated by an electric field to massive speeds, shooting this invisible beam into a strong magnetic field. What does the magnetic field do? It forces the flying charged particles to curve away from their straight path. And here is the main trick. Imagine a strong crosswind is blowing, and you simultaneously throw a heavy bowling ball and a light tennis ball forward. Obviously, the wind will blow the light tennis ball way off course, while the heavy bowling ball will fly almost straight. In the exact same way, A magnetic field bends the trajectory of light particles more strongly and has less of an effect on heavy ones. By measuring the radius of this curve, scientists were able to calculate the mass of individual atoms and nuclei with phenomenal, previously unimaginable precision. For creating this device and his subsequent discoveries, Francis Aston was awarded the Nobel Prize in Chemistry. Once they got their hands on such an incredibly precise tool, physicists started methodically weighing everything they could reach. And at first, everything went fine. They measured the mass of a single, free proton. They determined the mass of a single, free neutron. The numbers were laughably small, but they were specific and stable. And then the researchers decided to weigh a helium nucleus. As we remember, a helium nucleus, also called an alpha particle, has a remarkably simple and straightforward makeup. It contains exactly 2 protons and exactly 2 neutrons. It seems like nothing could be simpler. We have the exact weight of each individual part. We just take the mass of 2 protons, add it to the mass of 2 neutrons, and we should get the final mass of the helium nucleus. Simple arithmetic. The law of Lavoisier in action. 4 apples in a basket. But when Francis Aston and his colleagues ran the actual measurements of the assembled helium nucleus through the mass spectrometer, the results plunged them into a state of deep confusion. The numbers absolutely did not add up. The assembled complete helium nucleus turned out to be lighter than the sum of its individual components. The difference was small, about 0.7%, but for ultra-precise physics, it was a gaping, catastrophic canyon. Let's translate this paradox into the language of everyday reality so it makes sense. Just picture this scenario. You decide to build a car with your own hands. You go to a factory and order all the necessary parts. They deliver the engine, the body, the wheels, the windows, the seats, and every single tiny nut and bolt. You pile all these parts in your garage onto a massive, perfectly calibrated industrial scale. The scale reads exactly 1,000 kilograms. You write that number down in your notebook. Then you lock yourself in the garage for a few weeks and painstakingly, part by part, assemble your car. You haven't thrown away a single screw or a single scrap of wire. You used absolutely everything that was on the scale. And finally, the car is ready. The paint is shining. The engine starts. You drive this fully assembled, ready-to-go car back onto the exact same scale. And to your absolute shock, the display reads 900 kilograms. 100 kilograms of matter just evaporated during the assembly process. Where did the weight go? Did the wheels fall off? No, they're right there. Did the engine disappear? No, it's running. The car functions perfectly, all its parts are tightly bolted together, but it has somehow become lighter than the elements it's made of. In our macroscopic world, a situation like this seems surreal, breaking every conceivable law of logic. But in the harsh and bizarre quantum world, it is an absolute, fundamental reality. This phenomenon, discovered by researchers when weighing atomic nuclei, got an official scientific name: mass defect. Wherever physicists looked, whichever nucleus they weighed, carbon, oxygen, iron, or uranium, they always saw the same impossible picture. A nucleus always weighs less than the sum of its free nucleons. A fraction of the mass vanished without a trace the very moment the particles joined together into a single structure. But nature abhors a vacuum, and it doesn't let anything vanish without a trace. If the mass disappeared, it means it turned into something else. But into what? To solve this puzzle, we need to think back to the intense drama we talked about in the last chapter. Remember the unbelievable struggle taking place inside the nucleus. Positively charged protons feel a colossal electromagnetic hatred for one another. They repel each other with terrifying force. And to keep them together, the titans of the micro-world step in. The strong nuclear force. They deadlock the particles with invisible quantum rubber bands. Now let's ask ourselves a question. What does it take to overcome resistance and crush objects together that are fiercely trying to push each other away? It takes work. It takes spending energy. Imagine you're trying to compress a very stiff steel spring. As long as the spring is just lying relaxed on the desk, it's nothing special. But the moment you start squishing it with your hands, you are spending your physical energy. You're sweating. Your muscles are straining. And when you finally compress the spring to its limit and lock it with a latch, the energy you spent doesn't just disappear. It transitions into a hidden form. It gets stored inside that coiled steel spiral as potential energy. The spring becomes a vessel for that force, ready to unleash it at any moment if the latch gives way. When an atomic nucleus forms, something similar happens, but with a mind-blowing quantum twist. When protons and neutrons come together, answering the call of the strong force, they drop into a sort of energy well. They transition from a free, unstable state into a tightly bound, more favorable position. In that moment, the invisible quantum bands snap into place, locking the particles down tight. But nature is a strict accountant. For the system to shift into this stable, bound state, it is forced to give away a chunk of its energy to the outside environment. When a nucleus forms, a colossal amount of energy is released. That's the price of stability. That is the toll the nucleons pay to stay together, despite electromagnetic repulsion. Scientists call this value the binding energy of the atomic nucleus. But where do these tiny, lonely protons and neutrons get this energy to pay for their stability? They don't have external batteries or hidden fuel tanks. All they have is themselves. And this brings us to the most epic and counterintuitive conclusion in the history of science. To release this energy, the particles have to sacrifice the most precious thing they have, their very own physical flesh. That missing mass, that vanished 100 kilograms from our car analogy, didn't evaporate into some mystical ether. That missing mass is the binding energy that keeps the nucleus from falling apart. The physical flesh of the particles literally melted down into the invisible steel cables of the strong nuclear force. The mass effect is the visible, measurable on a scale proof that matter has been reborn as the tension of fields. Every atomic nucleus in the universe is basically a bank where a piece of the particle's primordial mass is locked away, converted into monstrous binding power. The tighter the nucleons are bound inside a nucleus, the higher the mass effect, and the larger the fraction of their weight the particles sacrificed for this quantum architecture. This realization shattered every familiar notion of reality. For thousands of years, people were absolutely certain that mass and energy were two completely different, unrelated phenomena. Mass was a property of tangible, heavy things, rocks, planets, iron weights. Energy was a property of motion, light, heat, fire, solid versus intangible, heavy versus elusive. It seemed unthinkable to merge these concepts. But the readings on Francis Aston's mass spectrometers were undeniable. On the deepest, most fundamental level of the universe's structure, the boundary between mass and energy blurs away. They bleed into one another, Like water pouring from one glass into another, matter can dissolve, becoming pure force, and force can freeze, gaining weight and shape. We have come right up to the answer of why a tiny atom creates such a massive explosion. We found the volt. We realized that inside that tiny speck in the center of the atom, the missing mass is locked away, transformed into tension energy. But one critically important, decisive question remains. What is the exchange rate? How exactly does one form transition into the other? Why does losing just a tiny fraction of a percent of mass generate a force that wipes cities off the map? To answer this question, science needed a genius capable of thinking completely outside the boundaries of human intuition. It needed someone who could write an equation tying together space, time, light, and the very essence of matter. We are about to unpack the most famous formula in human history. We'll talk about how Albert Einstein handed the world the key to understanding absolute destructive power in our next chapter. Let's pause for a second and try to wrap our heads around the worldview we just painted. In the previous chapter, we collided with the phenomenon of mass defect. We saw how harsh and unbiased instruments, mass spectrometers, proved the unthinkable. It turned out that when protons and neutrons merge into an atomic nucleus, a fraction of their physical mass vanishes without a trace. It doesn't just evaporate, it is smelted down into that exact colossal binding energy, into those invisible quantum rubber bands that lock the particles together against their furious electrical repulsion. This conclusion tore down a centuries-old wall that separated two fundamental concepts: tangible, heavy matter, and elusive, intangible energy. But in the early 20th century, when physicists were just starting to feel out this counterintuitive paradox in their labs, they didn't yet have the math to explain exactly how this transformation happens. They needed a precise mechanism. They needed a universal law for converting one entity into another. What's the exchange rate in this quantum bank? Exactly how much energy do you get from 1 gram of vanished mass? The answer didn't come from stuffy labs packed with complex machinery, but from a pure, unclouded leap of theoretical thought. In 1905, a young, completely unknown clerk at the Swiss patent office named Albert Einstein published a series of papers that forever changed the course of human history. In one of those papers, tackling the special theory of relativity, he derived a formula that every educated person on the planet knows today. This equation became the symbol of all modern science, its ultimate icon. You know this formula perfectly well, even if you've never studied physics. Energy equals mass times the speed of light squared. At first glance, this equation looks intimidatingly simple. Just 3 letters and a number. But behind this brevity hides the deepest and most terrifying truth about the nature of our universe. Einstein mathematically proved what researchers of the micro world had suspected. Mass and energy are not two different phenomena. They are simply two different states of the exact same fundamental substance. To grasp the true epicness of this statement, let's use a simple but very powerful analogy. Think of normal water. You can freeze it, turning it into a solid, cold, heavy block of ice. You can throw this ice, weigh it, or build an igloo out of it. Or you can heat this ice, and it will melt into liquid water, and then boil and evaporate, becoming invisible, hot, moving steam. Ice and steam look completely different. They have totally different physical properties, but on a deep, molecular level, they are the exact same substance. H2O. H2O. In the exact same way, according to Albert Einstein's genius insight, mass is just intensely concentrated, frozen, solid energy. And energy is liberated, active, evaporated mass. A rock lying on the ground, your smartphone, your own body. All of these are massive reservoirs of frozen energy, just waiting for their moment. But why don't we notice this energy in our daily lives? Why doesn't a rock explode in our hands? The answer lies in that mathematical constant on the right side of Einstein's equation, the speed of light. Let's look closely at this formula. The speed of light in a vacuum is the absolute speed limit of the universe. It's roughly 300,000 kilometers per second. That number alone is massive and hard to comprehend. Light can travel around the Earth's equator more than 7 times in just one single second. But in Einstein's formula, this giant number is squared. That means we have to multiply 300,000 by 300,000. And this is where the math enters the realm of absolutely chilling astronomical scales. The speed of light squared is a 9, followed by 10 zeros. That's 90 billion. This colossal multiplier is exactly what we have to multiply the mass by to find out how much energy is hidden inside it. Because this conversion rate is so monstrously huge, even the tiniest invisible speck of matter contains oceans of hidden power. Let's translate these abstract numbers into relatable everyday examples. Imagine a normal paperclip, a tiny piece of bent wire that weighs exactly 1 gram. You hold it in your hand. It seems totally harmless. But if we found a way to completely, without a trace, convert the mass of this single 1 gram paperclip into pure energy, according to Einstein's equation, it would produce an explosion of colossal magnitude. The energy released from this 1 gram of matter would be roughly equal to the energy released by detonating 20,000 tons of regular TNT. 20,000 tons of explosives is a massive freight train made of hundreds of train cars packed to the brim with dynamite. And all that unthinkable destructive power is sleeping inside one little paperclip, safely locked away in the form of mass. It was this very equation that became the missing key, finally allowing physicists to crack the mystery of mass defect in the atomic nucleus. When protons and neutrons combine, they lose only a tiny fraction of a percent of their original weight. But because Einstein's formula contains the speed of light squared, even this microscopic loss of mass turns into a colossal release of binding energy. This energy is so massive that it's more than enough to overpower the electromagnetic repulsion of the protons and lock the nucleus down tight with the strong nuclear force. Now let's put all the pieces of our puzzle together and look at the big picture. Over the course of 4 chapters, we've walked step by step down into the depths of the quantum world. We found out that the atom is almost 100% empty space. We learned that hiding in the center of this void is an unimaginably dense nucleus. We realized that inside this nucleus, a non-stop brutal war is raging between the 2 most powerful forces in the universe, the electromagnetic repulsion of the protons and the strong nuclear force pulling them together. And finally, we realized that this entire architecture holds together solely because of mass defect. Particles sacrifice a piece of their flesh, turning it into gigantic binding energy, as dictated by Albert Einstein's equation. An atomic nucleus isn't just a tiny ball of matter. It is an incredibly tightly coiled spring. It is a set trap holding colossal energy, released long ago when the nucleons merged. The nucleus is stable only as long as the quantum rubber bands of the strong force can withstand the pressure of the proton's electromagnetic hatred. And here we arrive at the main, fatal question of our story. What happens if this fragile balance is broken? What happens if we find a way to snap this quantum latch and let the spring uncoil? The answer is obvious. If the nucleus breaks, if the strong force weakens for even a split second, then electromagnetic repulsion will instantly take over. The protons, finally getting their freedom, will violently blast apart in all directions. And bursting out right alongside them will be that colossal binding energy that had been holding them back this whole time. The exact energy equivalent to the missing mass multiplied by a 9 with 10 zeros. Breaking apart just one invisible atomic nucleus can release millions of times more energy than any violent chemical reaction, like burning wood or exploding dynamite. That's because when dynamite burns, only the outer electron shells of the atoms are rearranging, while the nucleus stays untouched. Chemical reactions are just ripples on the surface of the ocean. But breaking a nucleus is unleashing the deep, primordial power of matter itself. But how do you break a nucleus? How do you shatter something held together by the strongest fundamental force in nature? It sounds like an impossible task. The strong force is so powerful that a person can't just take a quantum hammer and smash an atom to pieces. We needed a different, much more subtle and clever approach. Physicists started looking for vulnerabilities in this perfect architecture. They began studying different chemical elements, measuring their binding energy, and looking for weak links. And they found them. It turned out that not all atomic nuclei are equally tough. There is a limit to stability. There's a point where nature starts losing control over its own creation. A point where the nucleus becomes so bloated and unstable that the slightest nudge is enough to make it rip itself apart. We'll talk about how scientists found this limit and how heavy elements turned into a drop of water ready to burst in our next chapter. Let's stop for a few minutes and organize everything we've learned from our previous discussions. We've made a huge intellectual journey. We found out that matter is almost entirely made of a vacuum. We discovered an unimaginably dense nucleus in the center of that vacuum, where a constant battle rages between the electromagnetic repulsion of protons and the invisible quantum cables of the strong nuclear force. And most importantly, we understood that this fragile quantum architecture holds together purely because of mass defect. Particles sacrifice a tiny sliver of their flesh, which, according to Albert Einstein's grand equation, is smelted into giant binding energy that stops the nucleus from blowing apart. It seems like the puzzle is solved. The energy that fuels a nuclear explosion has been found. It's hidden inside every atom in the universe. But here, a curious mind will inevitably run into a very important and highly practical question. If absolutely every atomic nucleus is a compressed spring holding colossal reserves of binding energy, then why don't we build nuclear reactors out of everyday carbon, oxygen, or silicon? Why do scientists always need incredibly rare, heavy, and complex elements like uranium or plutonium to create atomic weapons or fuel for power plants? Why can't we just extract energy from a glass of water or a piece of wood? The answer to this question lies in the fact that nature is far from uniform in its creations. Not all atomic nuclei are created equal. Some of them are incredibly tough, perfectly balanced structures that are virtually impossible to break. Others are like flimsy houses of cards, ready to collapse from the slightest breath of quantum wind. To figure out exactly which atoms are good for releasing energy, Physicists in the mid-20th century had to map out the durability of the elements. Scientists started meticulously measuring the binding energy for every known chemical element. They took the total binding energy of a specific nucleus and divided it by the number of nucleons, meaning the total number of protons and neutrons in that nucleus. By doing this, they found a value they called the specific binding energy. To use a simple analogy, it's like calculating the average efficiency of every single worker at a giant factory. The higher this number, the tighter every individual brick is held in the overall structure, and the more stable the nucleus is as a whole. Physicists plotted the results of these massive calculations on a graph, and a breathtaking, profoundly meaningful picture appeared before their eyes. This graph was named the stability curve, or the curve of binding energy. Imagine this graph as a landscape. Right at the bottom, at the foothills, sits hydrogen, the lightest and simplest element, with just one proton in its nucleus. It has nothing to bind to, so its specific binding energy is 0. Then the curve shoots sharply upward in steep steps. Light elements, like helium, lithium, carbon, and oxygen, show a rapid spike in toughness as new nucleons are added. Their nuclei become more and more tightly packed. The curve keeps climbing until it hits an absolute peak, the summit of this quantum mountain. And sitting right on this summit is an element every one of us knows perfectly well: iron. Or to be super precise, the isotope iron-56, which has 26 protons and 30 neutrons in its nucleus. Iron is the gold standard of stability in our universe. It is the toughest, most energetically favorable, and flawlessly balanced mechanism nature has ever managed to build. An iron nucleus is so perfectly glued together by the strong nuclear force that it is physically impossible to extract energy from it by splitting it. On the contrary, to smash an iron nucleus apart, you'd have to spend a massive amount of your own energy and get absolutely nothing in return. That's exactly why iron is the end of the line in the life of any massive star. When thermonuclear fusion inside a dying star reaches the point of creating iron, the star is doomed. It has nowhere else to get energy from, and it collapses. Iron is cosmic ash, the totally inert and unbreakable foundation of matter. But what happens on our graph after the peak of the Iron Mountain? As we move toward heavier elements, to silver, gold, lead, and finally uranium, the curve of binding energy begins a slow but steady decline. The specific binding energy drops. Every single proton and neutron in these giant nuclei holds onto its neighbors a little weaker. The nuclei become loose, overcrowded, and internally unstable. Why does this happen? Why does nature lose its grip when assembling heavy elements? To crack this mechanic, we need to remember the fundamental difference between the two forces we've talked so much about. The difference between the strong nuclear force and electromagnetic repulsion. It all comes down to their range. The strong nuclear force, those invisible quantum rubber bands, packs colossal power, but it is extremely nearsighted. It can only reach its immediate next-door neighbors. Imagine a crowd of people in a packed bus. You can only tightly hold hands with the 2 or 3 people standing right pressed up against you. You have absolutely no way to reach someone standing at the other end of the bus. That's exactly how nucleons operate in an atomic nucleus. Every proton or neutron is bound by the strong force only to the particles physically touching it. Electromagnetic repulsion, on the other hand, works across huge distances. It knows no boundaries. It pierces right through the entire nucleus. Going back to our bus analogy, electromagnetic repulsion is like an unbearable smell or scorching heat. If someone in the back of the bus feels too hot, that heat will eventually reach every single passenger. Every positively charged proton in the nucleus feels electromagnetic hatred for absolutely every other proton, regardless of whether they are right next to it or on the opposite edge of the nucleus. In light elements, like oxygen or carbon, this difference in range doesn't really matter. Their nuclei are so small that every nucleon is right next to all the others. The strong nuclear force easily wraps around the entire structure, ruthlessly suppressing any electromagnetic pushback. But let's look at uranium. Uranium-235 is a true giant of the microworld. Its nucleus holds 92 positively charged protons and 143 electrically neutral neutrons. This nucleus is so massive by quantum standards that its physical size becomes a critical issue. Inside this giant nucleus, a proton on one edge and a proton on the opposite edge are separated by too much distance. The strong nuclear force between them is exactly 0. They can't hold hands. They can't glue the nucleus together. But they still furiously push each other away through the electromagnetic field because the size of the nucleus is no obstacle for Charles-Augustin de Coulomb's law. This creates a horrific internal imbalance. Inside a uranium nucleus, 92 protons are simultaneously trying to push each other away. And the further apart they are inside this huge nucleus, the harder it is for the neutrons to compensate for this repulsion using the strong force. The nucleus swells up. It's no longer a dense, tightly squeezed ball. It turns into a pulsating, loose, overstrained clump of matter that can barely keep itself from instantly falling apart. How did physicists visualize and describe this unthinkable quantum object? In 1939, two brilliant theoreticians, the Dane Niels Bohr and the American John Wheeler, proposed a mathematical model that is stunning in its simplicity and clarity. This concept was named the liquid drop model of the atomic nucleus. Bohr and Wheeler suggested that a heavy uranium nucleus doesn't act like a solid crystal or a monolithic rock at all. Instead, it behaves exactly like a drop of incompressible liquid. Think about how normal water behaves. Water molecules attract each other, creating surface tension. It's this tension that makes water bead up into round drops instead of spreading out into a microscopic film over any surface. In Bohr and Wheeler's liquid drop model, the strong nuclear force plays the role of that surface tension. It forms an invisible elastic shell around the nucleus, trying to keep it spherical and stop the nucleons from flying away. But inside this drop, a different force is raging. The positively charged protons, pushing away from each other, create massive internal pressure. This pressure tries to tear the surface tension apart from the inside, stretch the drop, and deform it. Let's picture this on a macroscopic scale. Imagine you haven't closed the kitchen faucet all the way. A drop of water slowly starts pooling on the metal spout. It gets heavier and heavier. The water's surface tension is fighting gravity with everything it has, trying to hold the drop onto the metal. You can watch this drop quiver. You can see it lose its perfect round shape, stretching into an oval. You can see ripples of tension run across its surface. It's balancing on the absolute edge. It has reached its critical limit. All it takes is a light breeze, a microscopic vibration in the air, and the surface tension fails, and the drop falls with a quiet splash. A uranium-235 nucleus is exactly that kind of overfilled, heavy, quivering drop of quantum liquid. It is oversaturated with protons. The internal electrostatic pressure inside it has almost matched the strength of the strong force's surface tension. This nucleus is in a state of profound instability. It is constantly shifting shape, stretching out slightly and squeezing back together. The spring is pulled to its absolute ringing limit. The latch is barely holding on. Niels Bohr and John Wheeler proved with their math. Heavy elements sitting on the right, downward slope of the binding energy curve are disastrously lacking in durability. Nature built them at the very limit of its capabilities, and they are ready to break. Scientists only had one step left to take. They needed to figure out a way to give this trembling drop a tiny nudge. They needed to find that microscopic pebble they could toss into this quantum swamp to upset the fragile balance and let electromagnetic repulsion rip the shell apart. And that tool was found. The irony of fate is that the key to destroying the nucleus turned out to be the exact same particle that was originally designed to act as the glue holding matter together. We are talking about the neutron. In our next chapter, we're going to head to the lab where one of the most fateful experiments in human history took place. We'll learn exactly how physicists figured out how to pull the trigger of the microworld, and why hitting a drop of uranium with just one uncharged particle releases a fire unlike anything seen before. At the very end of the last chapter, we left our story on an incredibly intriguing cliffhanger. We pictured the atomic nucleus of a heavy uranium element as a trembling, overstressed drop of quantum liquid. Inside this microscopic sphere, 92 positively charged protons are locked in a desperate, non-stop battle with the invisible bands of the strong nuclear force. This drop is stretched out, deformed, and unstable. Its internal electrostatic pressure has hit its absolute peak. It is balancing on the razor-thin line separating existence from immediate destruction. It became totally obvious to the scientists studying this phenomenon in the late 1930s that to pop this drop and unleash the energy locked inside, they had to disturb it somehow. They needed to find a tool, a sort of quantum hammer or projectile, to hit the uranium nucleus from the outside. The slightest external nudge would disrupt this fragile balance and allow the forces of Coulomb repulsion to tear the nucleus to shreds. But how exactly do you touch something that is billions of times smaller than a grain of sand? Physicists couldn't use normal tools. They needed something on the same scale as the nucleus itself. And the first candidates for these quantum projectiles were the particles scientists already knew pretty well by then. These were alpha particles, the same ones Ernest Rutherford used to discover the atomic nucleus in the first place, and free protons. Researchers started building the first particle accelerators, trying to speed protons up to massive velocities and fire them straight at a uranium target. The logic seemed flawless. If you shoot a proton into an unstable drop, the shock wave from the impact will force it to split. But nature had built an incredibly powerful line of defense along this path. The problem was electrical charge. As we remember perfectly well, a uranium nucleus has 92 protons, which means it carries a massive positive charge. A free proton, the projectile the scientists were trying to shoot into this nucleus, also has a positive charge. And the second this flying projectile got close to the uranium target, Charles-Augustin de Coulomb's law kicked in. To really visualize this hurdle, picture a steep, perfectly smooth hill. At the very top of this hill is a deep well. That's our atomic nucleus, where particles are held by the strong force. Now imagine standing at the bottom and trying to roll a heavy bowling ball straight into that well. Your bowling ball is the flying proton. You push it up hard. The ball rolls, but as it climbs, the invisible electrostatic force of repulsion gets stronger and stronger. It literally pushes against your projectile, slowing it down. In the vast majority of cases, the ball just loses its momentum, stops halfway up, and rolls right back down to the bottom without ever reaching the well at the top. Physicists name this invisible force field around the nucleus the Coulomb barrier. To smash through this barrier and force a proton inside the uranium nucleus, scientists had to accelerate the particle to totally insane speeds. They had to give the projectile kinetic energy in the millions of electron volts. 1930s technology simply didn't allow for making accelerators that powerful and precise on a large scale. It seemed like the nucleus was safely protected from any outside interference by its very own electromagnetic field. But there was a way out of this dead end, and it appeared thanks to the discovery made by the British physicist James Chadwick in 1932. Chadwick, as we discussed earlier, discovered the neutron. The neutron is a truly amazing creation of nature. By mass, it is practically identical to a proton, making it a heavy, full-fledged resident of the quantum world. But it has one fundamental feature that makes it the ultimate, unbeatable tool for hacking atomic nuclei. The neutron is absolutely neutral. It has no electrical charge, not positive, not negative. Going back to our analogy with the hill and the bowling ball, a neutron is a ghost. For a neutron, the Coulomb barrier doesn't exist. It doesn't feel the electrical field created by the uranium nucleus at all. Where a proton sees an impenetrable, steep mountain of resistance, a neutron sees a completely flat, smooth surface. It can just casually stroll across this surface and fall freely right into the well of the strong nuclear force. The nucleus simply has no way to push it away, because electricity has nothing to grab onto in a neutral particle. The first person to fully grasp the epic potential of the neutron as the perfect quantum projectile was the genius Italian physicist Enrico Fermi. In 1934, working in his lab in Rome, Fermi made a historic decision. He decided to methodically, step by step, bombard absolutely every known chemical element on the periodic table with neutrons, starting from the lightest and ending with the heaviest. Fermi wanted to see how the nuclei of different substances would react to having this neutral particle injected into them. During these grueling experiments, the Italian researchers' team made a stunning and, at first glance, totally illogical discovery. It turned out that for a neutron to successfully penetrate a nucleus, it didn't need to be accelerated to massive speeds at all. In fact, fast neutrons did a much worse job. The most effective tools turned out to be so-called slow neutrons. Let's break down why nature works this way. Imagine a hole on a golf course. That's the atomic nucleus. And your golf ball is the neutron. If you hit the ball with your club as hard as you can, it'll fly at huge speeds. Even if the ball passes exactly over the hole, it will just fly right over it without having time to drop in, because its kinetic energy is too high. But if you tap the ball softly, if it rolls slowly across the grass, then when it reaches the edge of the hole, it will gently drop in. In the exact same way, a slow neutron leisurely passing by an atomic nucleus has time to be grabbed by the invisible bands of the strong force and stays inside forever. Fermi figured out how to slow neutrons down by passing them through normal water or paraffin wax, which massively boosted the efficiency of his experiments. Methodically working their way through the periodic table, Enrico Fermi and his team eventually reached uranium. At the time, uranium, with its 92 protons, was the heaviest element known to science on the planet. The Italian physicists placed a chunk of uranium under a beam of slow neutrons and waited for the results. According to all the theories of the time, the uranium nucleus was supposed to absorb the incoming neutron. By becoming one particle heavier, it should undergo an internal transformation and turn into a completely new, never-before-seen, super-heavy chemical element with 93 protons. Fermi was certain he was creating new forms of matter, artificial transuranium elements that had never existed in nature. But the chemical analysis of the irradiated uranium yielded incredibly confusing and bizarre results. The scientists were finding traces of elements in the samples that didn't fit into their neat worldview at all. The radioactive background of the altered substance behaved totally unpredictably. Fermi published his findings, but the mystery of what exactly happened to the uranium nucleus in that moment remained unsolved for a few more years. The true picture of what went down was only revealed to the world at the very end of 1938, thanks to the brilliant work of German chemists Otto Hahn and Fritz Strassmann, along with a profound theoretical breakthrough by Austrian physicist Lise Meitner. Hahn and Strassmann were running experiments irradiating uranium with neutrons in Berlin. Being incredibly meticulous chemists, they decided to find out with absolute precision exactly what substances appeared in the sample after hitting it with the neutron beam. They ran highly complex precipitation reactions, trying to separate out the suspected new heavy elements. And to their absolute shock, they found barium in the irradiated uranium. Barium is chemical element number 56. Its nucleus holds exactly 56 protons. Meanwhile, a uranium nucleus, remember, has 92 protons. Barium is almost half the weight of uranium. Otto Hahn was stunned. How is that even possible? According to the laws of classical nuclear physics at the time, hitting a massive uranium nucleus with one tiny neutron could, at most, chip off a few protons. It was like throwing a small pebble at a brick wall and chipping off a piece of plaster. But the chemistry results undeniably proved something else entirely. The impact of a single invisible neutron didn't just chip a piece off. It chopped the giant uranium nucleus clean in half. It smashed the brick wall into 2 equal pieces. Not knowing how to interpret this physics-wise, Otto Hahn wrote a letter to his longtime colleague, Lise Meitner. At the time, Meitner, fleeing the Nazi regime, had been forced to emigrate to Sweden. After receiving the letter with the Berlin experiment results, she went for a winter walk in a snowy Swedish forest with her nephew, the young and talented physicist Otto Frisch. And right there, among the trees, sitting on a fallen log and scribbling on scraps of paper, Lise Meitner made one of the greatest discoveries in the history of science. She remembered the liquid drop model of the atomic nucleus proposed by Niels Bohr and John Wheeler. She pictured the uranium-235 nucleus as a giant, incredibly heavy, and tense drop of water. This drop, as we established in the last chapter, was balancing on the edge. The Coulomb repulsion of its 92 protons was tearing it apart from the inside, while the surface tension of the strong force was barely keeping it from falling apart. And then, Lise Meitner imagined what happens the moment a slow neutron seamlessly slips into this trembling drop. The neutron has no charge, so it phases through the Coulomb barrier like a ghost. But the second it crosses the border into the nucleus, it is instantly grabbed by the strong nuclear force. By getting inside, the neutron brings extra mass and, crucially, its own binding energy. This energy pours into the drop's already overstressed state. The impact of just one neutron turns out to be the proverbial final drop, that tiny nudge that was missing for a catastrophe. Getting this extra energy sends the uranium nucleus, now called uranium-236, into a state of frantic quantum excitement. The drop starts vibrating wildly. It loses its spherical shape. It stretches into an oval, then squeezes back, then stretches again, like a rubber ball bouncing between invisible clamps. At a certain point, the size of these swings gets so extreme that the nucleus stretches out into the shape of a dumbbell. Imagine an elongated peanut. Protons pool at the edges of this dumbbell, while a narrow bridge of quantum matter forms in the middle. And here comes the climax, the moment of total physical collapse. As we know, the strong nuclear force only works over vanishingly small distances. The second the bridge of this dumbbell stretches past a few femtometers, the quantum bands simply can't reach each other anymore. The surface tension snaps. The strong force loses control of the situation. The exact microsecond that bridge breaks, only one dominant force is left on stage: the force of electrostatic repulsion. Now we have two separate massive drops, for example, a barium nucleus and a krypton nucleus. Both of these drops have a colossal positive electrical charge, and they are now right up against each other. According to Coulomb's law, when two giant identical charges end up at such a microscopic distance, they start pushing away from each other with truly apocalyptic force. The invisible spring we've spent so long talking about finally blows its latch. The two fragments of the torn uranium nucleus push away from each other with monstrous fury. They fly apart in opposite directions at a speed reaching a massive fraction of the speed of light. Lisa Meitner, sitting in the winter woods, quickly ran the numbers using Albert Einstein's famous formula. She calculated the mass of the original uranium nucleus and the neutron, and then subtracted the mass of the resulting fragments. The result fully confirmed her guess. The fragments were slightly lighter than the starting material. That vanished mass, that mass defect, instantly converted into the pure kinetic energy of the flying pieces. The energy released from splitting just one nucleus was 50 million times greater than the energy released from burning a single carbon atom in a normal campfire. And just like that, humanity found the trigger. The neutron became the key that unlocked Pandora's box. Scientists figured out how to make a tiny particle pop and unleash the flame. But destroying one single nucleus is absolutely nothing on a macroscopic scale. The energy it releases is huge for a quantum particle, but to us, it's not even a mosquito bite. To create a destructive wave capable of wiping cities off the map, they needed to force billions upon billions of atoms to split all at once. They needed to find a mechanism that would turn a single flash into an uncontrollable avalanche. How physicists discovered the chain reaction, and how a single neutron spawns a storm, is what we'll talk about in our next chapter. We left off at a moment of epic scientific triumph. Physicists had figured out how to split the atomic nucleus. As we established, Lisa Meitner used math to prove that hitting an unstable drop of uranium-235 with just one slow neutron leads to disaster. The nucleus rips into two pieces, and that unthinkable binding energy predicted by Albert Einstein is unleashed. But let's be completely honest. Destroying one single invisible nucleus is a totally insignificant event on the scale of our macroscopic world. The energy released is only huge by the standards of quantum particles. If you split one uranium atom, you won't feel a thing. You couldn't even warm up a grain of sand with that heat. To create that crushing shockwave capable of turning concrete buildings to dust, scientists needed to force billions of uranium atoms to split almost simultaneously. They needed a mechanism that would turn a single quantum spark into an all-consuming wildfire. And this mechanism was discovered thanks to a sudden, almost mystical flash of insight by one brilliant man. In the fall of 1933, Hungarian theoretical physicist Leo Szilard was walking down the streets of London. At the time, the scientific community was actively buzzing about the earliest experiments with atomic nuclei. Szilard stopped at an intersection, waiting for the light to turn green, and in the exact second the light changed and he stepped off the curb, an absolutely terrifying genius thought flashed in his mind. He realized the concept of a nuclear chain reaction. Leo Szilard's logic was razor sharp. He asked himself one question: what if, when a heavy atomic nucleus rips apart, it releases not just the kinetic energy of the fragments, but also several new, free neutrons? After all, heavy elements, as we remember from Chapter 6, are overstuffed with this quantum glue. When a uranium nucleus splits in half, the pieces don't need that many neutrons to stay stable. That means the leftovers have to fly out. Szilard realized something terrifying. If one slow neutron hits a uranium nucleus, splits it, and in the process spawns two new, free neutrons, then those two new projectiles will keep flying. They will crash into two neighboring uranium nuclei. Those will also rip apart, unleashing huge amounts of energy and spawning 4 new neutrons. Those 4 neutrons will split 4 nuclei, spawning 8 projectiles, then 16, 32, 64, 128. It's classic geometric progression, exponential growth. To visualize this process, just imagine a massive room enclosed by glass walls. On the floor of this room, thousands of set wooden mousetraps are packed tightly together. Sitting carefully on each mousetrap are 2 light ping-pong balls. This is our uranium target. Now imagine you are standing on a balcony above this room, and you drop just one single ping-pong ball. Your ball lands on the first mousetrap. It snaps shut with a loud clack and launches its 2 balls into the air. Now there are 3 projectiles flying around. They land on the next mousetraps, which launch more balls. In a tiny fraction of a second, the entire room turns into a raging, chaotic storm of thousands of flying plastic spheres and non-stop snapping springs. That is exactly what happens inside a chunk of uranium during a chain reaction. If you gather enough uranium-235 atoms in one place, what's called critical mass, the process becomes totally uncontrollable and irreversible. Billions of generations of nuclear fission will flash by in millionths of a second. Every instant releases a tiny bit of binding energy, but because of geometric progression, the total energy released in a fraction of a microsecond hits astronomical numbers. A single quantum process balloons into a macroscopic cataclysm. An avalanche of energy breaks off its chain, and not a single law of nature can stop it. We get the math of a chain reaction. We understand how the number of split uranium atoms balloons exponentially. But there's another conceptual gap here we need to cross. How exactly does the invisible movement of quantum particles turn into that unbearable heat, that blinding flash, and that crushing shockwave we see in the macro world? How does abstract binding energy become tangible, incinerating fire? To answer this, we need to remember the fundamental definition of temperature. In our daily lives, we treat heat like its own independent thing. We feel the sun warming us or a hot kettle burning us, but from a strict physics standpoint, heat doesn't exist as a separate substance. Temperature is just a macroscopic illusion created by the chaotic, mechanical movement of microscopic particles. The faster atoms and molecules wiggle, vibrate, and crash into each other, the hotter an object feels to us. Absolute zero is a state of total rest, where all movement in the quantum world freezes, and millions of degrees is a state of frantic, uncontrollable, kinetic panic. Now let's jump back to the very epicenter of our atomic explosion, to that exact microsecond when the chain reaction hits its peak. Billions of uranium nuclei have just been ripped in half by a constantly multiplying swarm of neutrons. The invisible quantum bands of the strong force have snapped. The electromagnetic repulsion that was sleeping inside those nuclei for billions of years has finally broken free. The fragments of the torn nuclei, barium, krypton, and a bunch of other elements, push away from each other with apocalyptic force. They fly apart in different directions at speeds of tens of thousands of kilometers per second. This is colossal, unimaginable kinetic energy. But these fragments aren't flying through an empty void. They are surrounded by trillions of other atoms. Atoms of air, the metal casing of the bomb, the dirt. The uranium fragments hauling at near light speeds slam full force into these neighboring, peacefully resting atoms of the environment. It's like a hypersonic freight train crashing full speed into a crowd of people standing still. The kinetic energy of the fragments transfers to the surrounding matter. The surrounding atoms take a monstrous mechanical hit and start frantically bouncing around space themselves, crashing into their neighbors. The speed of the chaotic movement of particles in this localized spot of space instantly skyrockets to levels unimaginable under normal conditions. It is exactly this frantic, violent dance of collisions that our macroscopic world perceives as a massive spike in temperature. The matter at the epicenter doesn't just get hot. It cycles through every known state of matter in a millionth of a second. Solid metal melts, then instantly evaporates, turning into gas. But the kinetic energy of the particles is so high that even a gaseous state can't hold up. The atoms crash into each other so hard that electrons get ripped right off their orbits, leaving bare, red-hot atomic nuclei. The gas turns into plasma, the fourth state of matter. The temperature of this plasma at the epicenter of the explosion reaches tens of millions of degrees. That is hotter than the very center of our sun. At that heat, the plasma fireball starts blasting out a colossal amount of electromagnetic radiation, mostly in the X-ray and ultraviolet spectrums. This radiation shoots out in every direction at the speed of light. The surrounding air, soaking up these hard X-rays, instantly superheats and starts glowing with a blinding, unbearably bright white light itself. That's how the flash of light is born, capable of blinding anyone watching from dozens of miles away. And an unbelievable spike in temperature causes a spike in pressure. The plasma, heated to tens of millions of degrees, tries to expand instantly. It pushes against the surrounding, colder air with monstrous force, crushing it and packing it into an impenetrable wall. This wall of super-dense, compressed air starts roaring outward in every direction at supersonic speeds. This is the shock wave. A wall of density that flattens buildings, rips trees out by their roots, and turns stone to dust. All this fury, all this light and roar, it's all just the direct, mechanical result of tiny, positively charged protons finally breaking free from their invisible quantum leashes and hammering the world around them with their primordial mass. Splitting heavy uranium and plutonium nuclei is a truly terrifying and highly effective way to unleash energy. But nature, in its endless variety, kept another mechanism in store for us. A mechanism that doesn't destroy, but creates. A mechanism that fuels the entire cosmos with light and gives life to our planet. If we look back at that same curve of binding energy stability we discussed in depth in Chapter 6, we won't just see a gentle slope on the right, where unstable giants like uranium hang out. We'll also see an incredibly steep climb on the left. Sitting on the left side of the graph are the lightest chemical elements in the universe: hydrogen, helium, lithium. Their nuclei only have 1, 2, or 3 protons. The specific binding energy in these light nuclei is very low. Every nucleon inside them holds onto its neighbors pretty loosely, compared to the gold standard of iron sitting at the top of the mountain. And this leads to a brilliant and paradoxical idea. What if we went in reverse? What if, instead of breaking heavy, overstuffed elements apart, we did the opposite? Took the lightest, simplest building blocks of matter and forced them to merge together. In modern physics, this process is known as thermonuclear fusion. The logic of this process relies on the exact same ironclad law of Albert Einstein. If you take 2 protons and 2 neutrons that are either floating free or part of very light nuclei, and you somehow force them to stick together into one whole helium nucleus, that same mass defect happens. The assembled helium nucleus will turn out to be lighter than the sum of its original parts. And the difference in mass, according to the formula, multiplied by the speed of light squared, instantly turns into gigantic binding energy that bursts out as heat and radiation. Plus, the percentage of mass lost during the fusion of light elements is way higher than the percentage lost when splitting heavy uranium. Thermonuclear fusion is the most powerful, most efficient source of energy in the entire universe. It is the absolute pinnacle of energy evolution. But standing in the way of this energy source is an obstacle that classical physics considered unbeatable. Remember how Enrico Fermi struggled to punch through the Coulomb barrier? Protons have a positive charge. If you want to smash 2 hydrogen nuclei together, you have to get them within 1 femtometer of each other, so the quantum bands of the strong force can grab them. But the closer they get, the more furiously they push away. The electrostatic hatred between them grows exponentially. To smash through this invisible wall, the protons have to be accelerated to absolutely insane speeds. They have to be slammed together head-on with such crushing force that their momentum breaks through the electromagnetic resistance. And as we just figured out, particle speed is temperature. So to ignite the thermonuclear fusion reaction, you have to heat hydrogen to tens of millions of degrees. At those temperatures, atoms lose their electrons and turn into a boiling soup of naked protons. Plasma. In this hellish cauldron, the protons are zipping around so frantically that sometimes, when they crash into each other, they punch through the Coulomb barrier and fuse together. This exact process is happening right now in the very heart of our sun. The star's giant gravity crushes the hydrogen plasma into a super dense ball, and the temperature of 15 million degrees forces the protons to fuse, creating helium and radiating the exact light that warms the Earth. But back in the 1920s, scientists hit a wall. Physicists calculated the temperature inside the sun and realized that even 15 million degrees was disastrously short of what was needed to break the Coulomb barrier. The protons in the sun are moving way too slowly to crash together head-on. According to the laws of classical mechanics, our sun shouldn't be shining at all. The answer to this cosmic mystery was proposed by the brilliant theoretical physicist George Gamow. He applied the laws of quantum mechanics to the hearts of stars and described a phenomenon called quantum tunneling. In the weird world of quantum physics, a particle isn't a solid little ball. It acts like a wave. Its location in space is based on probability. Gamow proved mathematically there is a tiny, vanishingly small chance that a proton, even without enough energy to break the Coulomb barrier, can just materialize on the other side of that invisible wall. It doesn't jump over the wall. It passes right through it, like a portal. The odds of this happening for a single proton are basically zero. But inside the sun's core, there are so many protons, and they crash into each other so often that this highly unlikely quantum glitch is happening all the time. It is quantum tunneling, described by George Gamow, that lets our star slowly, evenly, and steadily burn its hydrogen over billions of years. Every particle of light, every sunbeam hitting your face, is the result of invisible protons in the distant abyss of space, cheating the law of electrostatic repulsion and giving up a piece of their mass in the name of light. Once humanity realized the colossal power of thermonuclear fusion, we immediately tried to recreate this stellar process on Earth. And unfortunately, the first attempt was a destructive one. Scientists built a thermonuclear bomb using a classic uranium explosion just as a detonator, a match to create the tens of millions of degrees needed for a fraction of a second to force hydrogen isotopes to fuse. The power of this weapon turned out to be thousands of times stronger than the first uranium bombs. But destroying things is the easy way out. The ultimate challenge facing fundamental science today is learning to control this starfire, to make it burn slowly and steadily, like in the core of the sun, to power humanity with endless, clean energy. Top-tier scientific journals like Science or Nature regularly publish papers about the massive efforts physicists are making to contain super-hot plasma. Think about the scale of the problem. We need to create a temperature of about 100 million degrees here on Earth. That is way hotter than the center of the sun, because on Earth, we don't have that colossal gravitational pressure. But what kind of container can hold something heated to 100 million degrees? Any material we know of, any metal, ceramic, or super strong alloy, would instantly vaporize the second it touched plasma that hot. A solution to this seemingly impossible problem was proposed in the mid-20th century by Soviet scientists Igor Tamm and Andrei Sakharov. They came up with a concept that became the foundation for the most complex engineering structures of modern times: tokamaks. A tokamak is a torus-shaped chamber equipped with magnetic coils. Tamm and Sakharov's idea is incredibly elegant. Since plasma is made of charged particles, naked protons and electrons, these particles are affected by a magnetic field. If you build a giant vacuum chamber shaped like a donut and surround it with unbelievably powerful superconducting magnets, the magnetic field lines will form an invisible cage. The plasma, blazing at 100 million degrees, will race in a circle inside this vacuum tube, trapped by the magnetic field. It will float in an absolute void, not touching the physical walls of the reactor by even a fraction of a millimeter. Today, a massive international experimental thermonuclear reactor is being built in France, the ITER project. It's humanity's attempt to literally hold a miniature star in magnetic hands. Dozens of countries have pooled their tech, money, and brains to force hydrogen isotopes to fuse and release their hidden mass as pure heat. Scientists are constantly upgrading the magnetic containment systems, using insanely complex computer algorithms to suppress the turbulence and chaos that break out in the roaring plasma. Every millisecond record of keeping that blazing cord of plasma contained makes global headlines. This is the absolute bleeding edge of human thought, a battle for an ultimate energy source that will one day permanently change the face of our civilization. Our long, deep journey into the deepest secrets of matter is coming to an end. We started with a simple, everyday question. Why is a tiny, invisible atom capable of spawning such a monstrous, city-flattening explosion? And now we see the answer in all its terrifying beauty. A tiny atom creates a huge explosion because inside it, past a thick layer of absolute quantum void, hides the tightest spring in the universe. The atomic nucleus is the arena for an endless war between two titanic forces of nature. On one side is the electromagnetic repulsion of protons, their wild, primal urge to fly away from each other. On the other side are the invisible steel cables of the strong nuclear force, which pull them together against all logic. We've realized that this fragile quantum architecture holds together purely thanks to mass defect. The physical flesh of particles is melted down into tension energy. The mass we are so used to in our tangible world isn't just weight. It is deeply frozen, solid energy, a relic from the era of the Big Bang, when our universe was infinitely hot and incredibly dense. By breaking apart an unstable uranium nucleus with the help of a neutral messenger, the neutron, we aren't creating new energy. We are just breaking the latch on an overstrained spring. We're letting Coulomb's law win, and the particles, finally getting their long-awaited freedom, crash into the world around them, turning their kinetic fury into blinding light and million-degree plasma. We've learned how to open this quantum Pandora's box. The human intellect, armed with math and curiosity, managed to reach into places where even light can't go. We uncovered the hidden mechanisms of nature capable of bringing absolute destruction. We turned Albert Einstein's equation into a tool that alters the course of history. But those exact same fundamental laws, that exact same conversion of mass into energy, also govern the glowing of distant stars in the night sky. The thermonuclear fusion powering our sun is the flip side of the exact same coin. Nature showed us both paths, the path of splitting the heavy and the path of fusing the light. We are standing on the edge of the greatest transition. The only question is whether we, as a species, can finally tame this primordial starfire. Will we be able to hold the furious plasma inside the magnetic traps of our tokamaks so that the energy of the quantum world stops being a threat and turns into an endless source of creation for future generations? What will be humanity's next step in understanding this limitless power hidden in the void? The answer to that question will have to be found by those who look up at the stars today and keep asking questions.